Hello viewers, welcome back to the course on matrix computation and its application. So today lecture we are going to introduce two other subspaces based on the given matrix of order m cross n. So let's start with that. Now suppose we have a linear function f from Rn to Rm, and in this case I will define a set n of f. So this is set of all the elements x from the domain that is Rn such that f of x becoming 0, because I know that Rn and Rm are the vector spaces. So that is going to have a 0 element also. So in this case we are going to introduce taking all the elements from this domain which maps to 0. So maybe I have some, this is my Rn, this is my Rm, and I define a linear function f. So it maps that maybe this is my 0 element. So I will take this element maybe x1, then x2 is also going, x3 is also going, this element is also going, this element is also going to the same element 0. So I just taken these elements belongs to the Rn, and that is my set, I call it nf. Okay, so now the question is that this is a subset of Rn. Now I want to check, we want to show that nf is a subspace of Rn. So let us do that one. So let x1 and x2 belongs to the set nf, which implies if they belongs to the nf, then f of x1 is 0 and f of x2 is 0. Now let us see what about x1 plus x2. Now what about f x1 plus x2? Let us check this out. Now this is a linear map, so it should be equal to f x1 plus f x2, because f is a linear function. So if it is a linear function, then f x1 plus f x2, and that is going to be 0. So which implies that x1 plus x2 belongs to the set nf. Also, for any scalar, f of alpha x1, so it is a linear, so I can take this scalar outside and that becomes x1, and this is alpha into 0 and that is 0, which implies that alpha x1 also belongs to nf. So these two properties are satisfying. Then other properties we know that it is automatically satisfied to check that it is a subspace or not. So from here I can say that n of f is a subspace of Rn. Okay, so that is a subspace of Rn. Now what is the, so n of f is a subspace and it is called null space of f, or also called kernel of the function f. So this is also called the null space of f or the kernel of f. Now Now, we know that the matrix A of order m cross n is also a linear function. So, I have taken f x as a x, where A is, so A we know that one, and it means that A is a linear function from Rn to Rm. So, which implies that I can take n of A is a set of all x belongs to Rn such that A of x is equal to 0. It means, which implies that I know that Ax is equal to 0 is a homogeneous system of equations. Okay. So, that shows that this will be equal to set of all solutions of this one. It means we are taking the homogeneous system equation and we find this different solution, and that solution make the set Na. So, that is a called null space of matrix A, and this is subspace of R. So, similarly, I just take A transpose, then null space of A transpose is a set of all y belongs to Rm such that A transpose y is equal to 0. Okay. So, that is also we can take, and this can also be written as y belongs to Rm such that y transpose A is equal to 0. I have just taken the transpose of this one. Okay. So, this is of course, it is subspace of Rm, because y is coming from Rm here. So, it is a subspace of Rm, and this is called, so this is called left null space of matrix A. Okay. So, this is called the left null space of matrix A, and that is equal to n A transpose. So, this is how we are defining this one. Now, so from here I can draw the picture of the subspaces that is attached with the matrix A. So, we have a matrix A. So, now suppose I take just I will construct one picture. This one. So, I suppose I take, this is my Rn and this is my Rm, and I take a linear map A. So, that is represented by the matrix M. So, I know that the range space of A is here, it is a subspace of Rm, and range space of A transpose is here, and now from here this null space is a subset of Rn, subspace of Rn. So, it is a null space of A, and here is the null space of A transpose. So, these are the 4 subspaces that is always attached with the given matrix of order m cross n. Okay, so, from here you can check that, and we have already discussed that all are the 4 subspaces, and 2 subspaces this belongs to the Rn and 2 other subspaces belongs to the Rm. Okay, so, this way we can find out this one spaces. So, let us take one example. I have the matrix A, it is 1, suppose I take the simple matrix 1 2 3 and 2 4 6, suppose I just take the simple matrix, and this is of course 2 cross 3 matrix. So, I have a linear map R from R3 to R2. Now, so using this matrix I just want to find out its null spaces. Okay, so, let us do that one. Now, first what I will going to do is that I just take A x equal to 0, the homogeneous system I will take. Okay, so, that gives me 1 2 3 2 4 6, and that is x1 x2 x3, because it is coming from the R3, and that will be equal to x1 plus 2x2 plus 3x3 and 2x1 plus 4x2 plus 6x3. So, this is a vector I am going to get, and that is of course, it will be 2 cross 1. So, it is just belongs to the R2. From here you can see that now I have put this equal to 0, because I have to take it equal to 0. Now, we can see that the R2 is 2 multiple is, so R2 is 2 times R1, that we can see from here. Okay. So, from here I will get x1 plus 2x2 plus 3x3 equal to 0, and I will get 2x1 plus 4x2 plus 6x3 equal to 0, and from there I can just multiply this with the minus 2 and add here. So, I will get this system x1 plus 2x2 plus 3x3 equal to 0, all other things will be 0. So, basically if you take the matrix A and convert into the row echelon form, so you will get the matrix 1 2 3 and 0 0 0. So, this is my U, or maybe reduced echelon form, that is EA. So, based on this one I get this value. Now, from here you can see from here, now rank of A is also coming 1, right, and I also know that this x1 x2 x3 belongs to R3. So, from here I will just take the help of my knowledge based on matrix theory. Now, one thing is true, that we also know that the system Ax is equal to 0 is always consistent. Why it is always consistent? Because I know that 0 element is always there in the R2, because that is a vector space. So, it means I am taking the image of A, and this is just the linear combinations of the columns, and that is equal to 0. So, 0 is always there in the given subspace, any subspace. So, it is always consistent. So, it is a consistent and rank is coming 1. So, it will have infinite number of solutions. Okay. So, from here I can say that the system Ax equal to 0 is going to have infinite many solutions, because rank of A is equal to 1 and the number of variable is 3. So, by the way, for any value, even if the rank is 2, then still it is going to have a infinite many solutions. So, based on this one, now I get x1 plus 2x2 plus 3x3 equal to 0. So, from here I can take, now from the previous one, it is my, so this is my pivot. So, this is basically a basic column, and these are the non basic columns. Non basic columns. Now, we need to find out the free variable. So, number of free variables is always equal to number of variables minus rank. So, number of variable is 3 because coming from the R3, minus the rank is 1, so it is 2. So, we choose 2 free variable corresponding to non basic columns. So, the non basic column is coming from here, that is the second and the third one. So, from here I can say that, so my Ax is going to be, now from here, so what I can write down is, I can write my x1 is equal to minus 2x2 minus 3x3. So, my solution x1, x2, x3 can be written as, x1 is minus 2x2 minus 3x3 and x2 is x2 and x3. So, now you can see that there are 2 free variable x2 and x3. So, this is the solution. Now, this can be written as, I can take x2 common. So, it is minus 2 1 0 plus x3, that is minus 3 0 1, where x2 and x3 are the free variables and belongs to the real line, because we are taking coming from the vector spaces based on the field that is real line. And from here I can say that this is equal to the span of minus 2 1 0 and minus 3 0 1, and this is basically, if you take the span, that is equal to the null space of. So, now from here I am taking from the corresponding rows. So, that is the null space of A, because coming from the A. And now these two vectors, if you see, So, this is basically linearly independent, that you can check from there. So, now from here I can say that the dimension, so I can say that the set -2 1 0 containing two vectors -3 0 1 is a basis of NA. So, that is a basis, and from here it only has the two independent linear independent vectors. So, from here I can say that the dimension of NA is 2, and that is called nullity of A. Okay, so, this is called the nullity, like the rank. So, it is a nullity. So, the dimension of the null space is called the nullity. So, that is 2, and it is coming from the by solving this way. So, I know that range space of A and NA is coming from this one. Now, the next question is that we are able to find the nullity of A, then how we can find the null space of A transpose. Now, we want to find null space of A transpose. Now, the null space of A transpose, so in that case first I will define the A transpose. So, A transpose will be 1 2 3 and it is 2 4 6 and it is 3 cross 2. Now, I need to take A transpose Y. So, this one I can write as 1 2 2 4 3 6 and Y will come from Y1 Y2, that is it. So, this is basically 3 cross 2 and this is 2 cross 1 and that should be equal to 0 0 0 3 cross 1. So, now this Y will definitely come from R2. So, from here you can check that this become Y1 plus 2 Y2 is equal to 0, 2 times Y1 plus 4 Y2 is 0, 3 times Y1 plus 6 Y2 is 0. Now, from here you can check that since R2 is 2 times R1 and R3 is 3 times R1. So, from here you can see that these two rows are redundant. So, this is redundant rows, it means that does not make any sense. So, from here if you convert this matrix A transpose into the echelon form, so my A transpose convert to, so it become 1 2 0 0 0 0. So, that is basically my E A transpose or the echelon form, and from here you can check. So, now the rank of A transpose is 1 and that also I know that this is equal to the rank of A. So, from here I can say that only one equation y1 plus 2 y2 is equal to 0, that is going to be to play the role to finding the solution. Now, from here, so and definitely it is going to have, because we are now dealing with two elements, so it belongs to R2. So, y1 y2 and only rank is 1. So, from here I can say that the number of free variables is equal to number of variables minus rank. So, it is 2 minus 1, that is 1. So, one free variable is needed. So, from here I can say that A transpose y is basically equal to 0, that gives me y1 y2 becomes. So, y1 I can write now from here, it is my basic variable and this is non basic. So, this is my basic column and this is non basic column. So, from here I can write my y1 in the terms of the non basic. So, y2. So, I can write my 2 y2 because coming from here, and y2 is always there, and that I can write as y2 minus 2 1. So, that is always I can write, and y2 belongs to R2. So, I can write this is equal to the span of the vector this one, where y2 belongs to the real line, and now it is linearly independent. So, from here I can say that this is equal to the, so the set with one vector is a basis for null space of A transpose, and that also we know that it is a subspace of R2, because we have started with the matrix this one. So, it was from R3 to R2. So, from here I can say that this null space of A transpose belongs to this one and it is spanned by this. Now, so based on this we found that the null space of A is dimension 2 and the null space of A transpose is of dimension 1. So, I can say that its nullity of A transpose is 1. So, now from here I have a that was my 2 cross 3. So, moving from R3 to R2, we found that the null space of A, so that is the null space of A we have found, and that has the dimension 2. So, null space of A is dimension 2, null space of A transpose having dimension 1. So, it means nullity of A is 2, nullity of A transpose is 1. So, that we have seen. Now, we have also seen the rank of A is 1, that we have already seen, that this was the matrix coming from here, and then we found that its rank is just 1. Now, the rank of A is 1 and that is also equal to the rank of A transpose. So, both in both the case that is coming 1, and also we know that the range of A transpose, so dimension of this one, dimension of range of A transpose is equal to the rank, or dimension of range space of A is also equal to the rank, because the rank of A and A transpose is same, and from here you can check that this is equal to 1 and this is equal to 1. So, it means I have now from here you can check that rank of the matrix A plus nullity of the matrix A. So, nullity of the rank of the matrix A is 1, okay, and the nullity of the matrix 2. So, that is equal to 1 plus 2, that is equal to 3, and that is equal to the dimension of R3. Also, rank of A transpose plus nullity of A transpose. So, the rank of A transpose will be same, and nullity of A transpose just we have seen, that is equal to 1. So, that is equal to 2, and that is the dimension of R square. So, the picture I have made this one. So, from here you can see that in the case my RA is 1 and NAT is 1. So, it is 2, and this, because this will be same. So, it is 1 plus 2 is 3. So, that is with this one. So, now from here after doing this one we can make some conclusion. So, now some conclusion is there, that I will discuss another term, 0 null space. So, if null space of a matrix A that contain only one element, that is 0 element, then it is called zero null space. And now from here you can check from here this one. Now, in this case my null space is not the 0 element, containing not the 0 element, not even here, not even here. But what will happen if the rank of the matrix becomes 2? Now, if the rank of the matrix become 2, so in that case you will see that it becomes 2, then we have to make the changes in the nullity of this one to satisfy this condition. So, we will see this one in the next lecture, that how we are going to take this 0 null space whenever we are dealing with the subspace null space of the matrix A. So, let me stop here. So, today we have started with the other two subspaces, that is the null space of the matrix A and its transpose, that is A transpose. And then we have taken one example and show that how we can find the null space of A and null space of A transpose. So, in the next lecture we will continue with this one. So, thanks for watching. Thanks very much.